So I have a counting problem here. We have three people, and they're going to be sitting at this table, and I want to know how many different ways there are to arrange them. Well, it maybe sounds a little familiar because we've done questions very similar to this where we were seating people in a row, and that was it's a really pretty straightforward application of the multiplication rule. It'd be 3 factorial, which is 6. But there is a little issue here. There's something a little unusual is going to happen when we start to go in a circle instead of a straight line. So let's see how this is going to work out. Let's say we have three people that we're seating here. We'll call them A, B, and C, and I'm going to put some seats here. This will be seat 1, seat 2, and seat 3. Okay, so if we're doing this just kind of the old-fashioned way we did when we're talking about the multiplication rule, one permutation would be A, B, and C. So we're putting A in seat 1, B in seat 2, and C in seat 3. All right, now let's try another one. All right, I'm going to put my 3 seats here again, same places. Okay, how about C, A, B? That is a different permutation. For using the multiplication rule, these two are getting counted separately, right? But now let's see what happens if I put C here, A here, and B here. We run into a little issue. I want you to compare these two seating arrangements. At first glance, it might appear that they're different, but if you look at the people, right, in this first arrangement, person C has person A on their left and B on the right. Well, if you look at this second one, person C has A on their left and B on the right. And the same thing holds for persons A and B, right? Because if, again, compare these, just compare the two permutations. Compare the two seating arrangements, right? If I take the first arrangement and just rotate it, rotate everybody 120 degrees or one seat to the left, you get this permutation. And I don't want to count this second one separately because this really is the same thing. As far as these people are concerned, you're still sitting next to the same people. Nothing has changed. Right, so I want to do one more of these. Right, look at BA, well, not BAC, excuse me. Look at BCA. Right, now I have B here, C here, and A here. So that I did it again. Right, I took this second permutation, I rotated it 120 degrees. Everybody moved one seat to their left. Right? So in the end, everything stayed the same. All right, so how can I fix this? Right? How can I fix this and get to my answers? Well, we're going to do this in a way that's similar to what we did when we were deriving the formula for permutations. In a sense, we're overcounting here. Right? This particular permutation got counted 3 times where I really only wanted it to count once. And this is going to happen with every permutation, right? Every permutation is going to be rotatable, and every rotation is just going to be a duplicate. Well, how many rotations do I have? Right? Well, for every possible really unique permutation, I have 3 permutations around the circle. So if I take my 6 factorial, excuse me, not 6 factorial, 6 is the answer. If I take my 3 factorial that I get from the multiplication rule, and I divide it by 3, that's the number of seats. Right? Then I get, this is 3 factorial is 6, that's where the 6 came from. 6 divided by 3, and there are in fact only 2 distinct arrangements of people around this table. If you think about that, it's nice we've got a small number here. You can think about it a little intuitively. A can have one of 2 people on her left, either B or C, and once you pick that person to be on her left, the person on her right is determined because there's only one person left. All right, so with a small number like this, you can kind of talk your way through it intuitively, see that, yeah, okay, that is giving us the result that we need here. Okay, so this generalizes my conclusion there. Let's say we're arranging n objects. Well, the multiplication rule says there are n factorial possibilities, but each permutation has n identical rotations around the circle. So the number is actually going to be n factorial divided by n, and n factorial, that's n times n minus 1 factorial. So that's over n. Yeah, the n's cancel, and that's where n minus 1 factorial comes from for our formula. So I have an example here for us to look at, and you can see how it's going to involve our circle formula. We're seating people in a circle, but instead of seating individuals, we're seating couples, right? And we do have a restriction here. Each member of each couple pair has to sit with their partner. So how many ways can we do this? Well, I've talked about this before. When you're answering these counting questions, it's helpful to think in terms of choices, right? Because if you can come up with a list of choices that you have to make, and the choices are all independent, then you can bring the multiplication rule out, multiply them all together, and you get your answer. Right? So what choices are we making here? So my first choice is going to be how to arrange the 5 groups. Right? I'm not really thinking about seating people at this point so much as I'm thinking about how can I seat the couples. Right? Then choice 2, how to seat couple 1, for example. And there's only 2 choices here. I can do A1, A2, or A2, A1. Either way. Then I'm going to do this again. C3 is how to seat couple 2. And I've got the same 2 choices here, B1, B2, or B2, B1, and so on. I'm going to do this 5 times. So there's going to be C4, C5, and C6. And these are all going to be the same. There's going to be 2 ways to make each of those choices. So that leaves me with counting choice 1. Well, this is where we're going to use the group formula. We're seating 5 people in a group, so the number of arrangements here is going to be 5 minus 1. That's 4 factorial, which is 24. And that's what I need to know. Right now I can get my total number of arrangements by multiplying these together. This is 24. There's 5 2's there, right? So this is 24 times 2 to the 5th. 2 to the 5th is 32. So you get your calculator out. 24 times 32 is 768. And there's your answer. 768 different ways that we could arrange these 5 couples. So that's one new tool added to our toolbox. Right now we know the difference between a linear arrangement and a circular arrangement, how to calculate each case. In the next lecture, we're going to look at another scenario where the multiplication rule works. It's actually going to be our permutation formula that works, but we are going to have to modify it a little bit. We're going to look at the case where some of our objects are indistinguishable. For example, we can't tell them apart. For example, what if you have the letters in the word giraffe, and we want to rearrange them? Well, if all the letters were different, then it would be a very simple application of the multiplication or the permutation formula. But because we can't tell those F's apart, right, we're going to have to tweak it a little bit to account for that, and that's what we're going to talk about next.